So yeah, I just want to review a bunch of stuff. Stop me at any point, ask me about stuff. This is meant to be for you. So yeah, let's talk about non-programming stuff, then we'll talk about Python. Okay, so things that you are not allowed to forget. Kantianism, let's talk about our boys, right? Ethical theories. So Kantianism was the first thing that we studied about ethics. That was the first flavor of it, our first ethical theory. So ethics, by the way, is just the study of what's right, what's good, what should we be doing, and how can we justify that. So Kantianism is one way of viewing the world. Kantianist perspective. So what Kant thought, it was a dude, that was his name, and what he thought was that you would want to act in a way that you'd want everyone else to always act. So kind of like a golden rule. And always was the key, of course, with Kantianism, wasn't it? It was always like, you better act this certain way, and you can never change. Nobody gets any special exceptions. No special exceptions. Look like an eye. No special exceptions for you or for anybody else. So, yeah. And then also Kant thought that you should never treat somebody as a means to an end. You should treat them like a human being with their own wants and desires. Don't use them. And he kind of tried to argue that these two ideas were the same, in fact. So, yeah, that's the idea. And then the standard example for Kantianism is lying. If you were trying to, with a Kantianist perspective, trying to dissect the idea of lying, you would discover that you would say, no, I don't want to lie. I will never lie. A Kantianist would never want to lie. And the reason why is you'd think, what would Kant do? Would you want everyone to always be lying to you? And the answer is, of course, no. So that means you should never lie, according to Kantianism. Even if there is a situation where you really want to probably lie to save somebody, no, under Kantianism, you're never allowed to lie. It's like you would want to lie to a murderer who's trying to kill your friend and asking you where they live. So most people would want to lie in that situation, but Kant would say no. He has one thought about everything, no special exceptions for anything. All right, so that's maybe where Kantianism breaks down, but it's a good way to view things. It's a good way to come up with your idea, your answer to this ethical dilemma. Another example is stealing. I gave you that at the start of the semester, right? To Kant, it's a very easy question. Would you want everyone to always be stealing, especially from you? The answer is, of course, no. And so Kant would be against stealing, just like he would be against lying, even if it meant to feed your family. If there was no other way, someone was going to starve because unless you stole, Kant would still say no, you shouldn't do that. So yeah, that's Kantianism in a nutshell. Hopefully that's coming back to us. And then on the flip side of that was a bit more of a bendable theory. It was utilitarianism, right? A proponent of that was John Stuart Mill, so that's our other guy. And utilitarianism was all about utility. It's right there in the word, right? You want to maximize the utility / happiness / pleasure that you can possibly produce for any potential action you might want to make. And you're trying to decide whether or not to do something. You're measuring it not in terms of yourself. It's not from your perspective. It's the utility for everyone as a whole. Happiness for everyone as a whole, right? So again, you are not special under utilitarianism, for everyone, not just yourself. It does become hard to measure. So again, it's all about the consequences of an action, all right? All about the consequences. So if I do this thing, what's going to happen? What's going to follow from it? Versus if I do this other thing, what's going to follow from it? And again, maximizing the utility for everyone as a whole. So you're trying to decide, is thing X good or is thing Y better than it, etc., etc. You start to think about all the different ways, all the different things that could happen, all the different consequences of doing thing X. These things would happen if I did thing X. And these are the good things versus the bad things. And then thing Y, if I did thing Y, these things would happen, and these are the good things. And maybe they outweigh the X's. So you'd be I'm going to do Y instead. That's the idea. That's what you'd think under utilitarianism. And so a standard example of utilitarianism is that a utilitarianist would want to kill somebody, right? To kill one person to save 50 people, because they're gonna weigh that. If that's what you're forced to do, they would always rather kill one person rather than stand on the side lions and let 50 people die, okay? In most cases, okay? Assuming you're doing the weighing properly, because assuming all lives are equal, right? 50 lives is better than one life, so I'll have blood on my hands then. I will murder one person to save 50. Okay? Any questions about any of that? It's making enough sense. Coming back to us. So yeah, don't forget about that. That will be useful when you're analyzing stuff, coming up with your own ideas. So another thing that I want you to never forget is the idea of a fallacy, right? We had a big long essay about that. So what was a fallacy? It was when you make a mistake when you're reasoning about something, when you're arguing. And a fallacy is an error in your argument, and that means your argument is immediately false and you cannot trust it. You have to find a new argument, all right? So I'm sure we just had Thanksgiving, right? Maybe you had those political debates that some families like to have with distant relatives, and usually those kinds of debates among family members are full of fallacies, and maybe you've caught some of them this year if you do that. So yeah, it's error and reasoning / argument. It's all about argumentation. And one thing that's very key for this class is that every fallacy has a name. If you tell me something has a fallacy, you can't just stop there. You have to tell me what kind of fallacy, right? Otherwise, I won't believe you. So there were a bunch of different kinds of fallacies that we learned about. You discovered some more on your own, but I found some memes on the internet, and I put those as examples on this slide. Here are 3 examples of fallacies, each different kinds, and let's go through them. Just to remember some of them. So false dilemma. Remember that one? That was false dilemma, false dichotomy. It's like somebody's trying to tell you that you can do this thing or this thing, when in reality there's probably a secret third thing or fourth thing somewhere. So here's the silly meme example that I found on the internet. Like, well, you press the button. You get $50,000 if you press the button, but the person you hate the most gets $100,000. And so that's like a false dilemma. Like either you press the button or you don't, and like something good happens to the person you hate. Maybe you don't want that. And then the meme is like, I'm going to get $150,000 because I hate myself, right? So that's a false dilemma. That is a fallacy. You found a secret third option if you hate yourself. It's trying to say like either you get $50,000 and somebody else gets more, or you get no money at all, when in reality you could get all the money. Yeah. So that's a silly example of a false dilemma. I hope you see that. And just yell at me if you have any questions about this stuff. False dilemma was all about somebody's telling you got options 1 and 2 to choose from, but really, no, that's not all there is. There's an option 3 sitting somewhere. That's the idea. So yeah, go back to the slides. Go back to Wikipedia. All fallacies have names, though. Here's a straw man fallacy. Remember that a straw man fallacy is like putting words into somebody's mouth, saying something. It's trying to make an argument that somebody else is not actually making. It's easier to shoot down some. It's like you're turning their argument into straw, when in reality that's not what they were saying at all. You're just trying to find something easier to shoot down, putting words into somebody's mouth. So here's a silly example of a straw man fallacy in meme form. So back during COVID, Austria banned gatherings of more than 5 people, just as a means to prevent the spread of COVID. And so the meme was like, families of 6 have to shoot somebody. You can't all be together. And so the straw man fallacy is like, somebody's trying to say, like, obviously this ban is horrible. They're splitting families up. They can't even be together now. When in reality, the ban was on gatherings in the public, right? Public gatherings, not like familial gatherings. If you have 6 family members in the same house, that's fine. You have 6 roommates, that's totally fine. It was all about people that you wouldn't get in contact with normally, right? So do you see how that's a straw man kind of fallacy? This kind of quote down here. Putting words into somebody's mouth. That's not what Austria was trying to ban at all. Yeah. So that's the idea there. Straw man fallacies. And then tu quoque is a fun one. Just fun to say. It's Latin for you too. You too. And that's when somebody, here's the funny meme about it, but that's, again, the tu quoque fallacy is when somebody, let's say, I don't know, I don't know which perspective to give this from. Let's say that somebody is making an argument towards you, and they're saying, you should not be doing this thing, and they're telling you why, and like, they have a point, but then you turn around and you say, You know, you did that thing too. How dare you criticize me? That's what the tu quoque fallacy is. It's like trying to deflect the blame that is rightfully on you. Like, you shouldn't be doing this thing. Neither of you should have done that thing in the first place. That's what tu quoque is all about. So it's, I guess the standard example is like politics. Like, we say something, like we say, you did something bad, Russia, you shouldn't have done that. And then Russia's like, you did this bad thing too back in the day. Don't you criticize me. So when in reality, nobody should have ever done that bad thing. Okay. Those are 3 silly meme examples of fallacies that we've talked about. There are, of course, plenty more. Any questions about any of that? All right. So, yeah, let's switch gears to programming now. I think the rest of these slides are going to be about programming, have some cool examples. But yeah, we're going to talk about Python because I will be asking you to program on the test. All right, so get ready, get comfortable on your computer before you start the test. When you get to this room, like make sure idle is installed. Make sure everything's ready for you because you're going to be like copying and pasting the programs that you write into Canvas. It's like a little Canvas text box. So like instead of an essay for one of the text boxes, it's like you're going to type your code. So be ready for that. And so yeah, we're going to talk about Python so that you're ready to take the final. So I've been nice. I made you a cute little cheat sheet with some Python concepts that you can use on the final. It'll be included in both of these lectures. So like once I release this lecture slides today, you'll just go to lecture 30, and in addition to the slides themselves, which I still have to upload all this stuff, you'll see this CSCI 1 final cheat sheet file. You can go ahead and open that. You don't have access to it yet. I haven't released the lecture, but when I do, you'll have this too. And so here's a nice little page with a bunch of different stuff. Some color-coded examples of conditionals. So if else, if else, some loops, while and for, and functions, how to write them, define them, how to call them. And so hopefully you find some use in that. I tried to make it pretty and color-coded and like have little diagrams for how all this stuff is going to run. So you're welcome. And let's use this as we review. So let's talk about Python. Let's get at the first initial stuff that we first learned about: variables, types, operations. There's a bunch of different things, right? So I guess the first thing that we talked about was like variables and types themselves. So like when you make a variable, or you just like insert values somewhere in like a math statement, the things that you write down, they're of some implicit type that Python can figure out, right? Like ints. You remember the difference between ints and floats and bools and strs and all those things? Those are types of things. So like I think of them as clouds. Like when you make an int in Python, what kinds of things can be ints? Those are whole numbers. Those are like 0 and 1 and 42. Negative is fine too, negative 55, but whole numbers, no 0.5 or anything like that. Floats are the numbers that can have decimal points, okay? And the types kind of dictate how you can work with the data. Like, what can you do to an int? You can add 2 ints together, you can multiply them, divide them. That's a little bit different than like str, right? Strings, you can do multiplication on strs too, and I'll show you that. But it kind of duplicates the string. It doesn't do like math. Yeah. So like there's your int cloud, the bool cloud. You remember that? That's a very tiny cloud. What are the things that are bools? It's just true and false. You got your true, capital T, and then false, capital F. And everything that turns into a bool must turn into either true or false. So yeah, let's talk about all this. I'll make a new file in idle for this. That will also require me to figure out what lecture number we are today. So this is lecture number 30. I think that is correct. No, it is not. It is lecture number 31. That's what I thought. So I did not number these correctly. Let me fix that right now. Boop. Okay, so this is lecture number 31. And I'll make a folder for that. And a new file in that folder. Okay, so I'll save this. Lecture 31, that's where I'm trying to go. On my desktop. And I'll call this first file just like something simple, Python stuff.py. So yeah, let's write some code. So let's see. Yeah, let's talk about variables just in general before I write code. What is a variable? It's just a box that holds something, right? Like I can say give a name and then you put equal sign, and then you give it what you want it to hold. So x equals 42, for example. That creates a box that holds onto the value 42. So now if you say x all over the place, it will be replaced with 42 in your larger contexts. So same with making like a float variable, y equals 3.14. That will make another box, and this holds a float this time. And it holds 3.14. Okay, and then you can use that in a larger place. Just given stuff that you don't want to type again, a name. So that's easier to reason about. So let's make a variable, x equals 42. So that'll make that box, and of course now you can use x as if it's word 42. It's going to get replaced with it. So print x, that'll print 42. Python knows the type of all your variables, so like type of x, what is that? It'll give us int. And then you can do math stuff with ints, right? You can print like x plus 2, you can print x times 2, you can print x squared, that's the double star. If I run this, you get exactly what you would expect. So 42, it's an int, and then we get 44, 84, 42 squared is 1764. Cool. But yeah, that's variables in a nutshell. And types, right? Python has types. Thinking about that all the time. And floats, right? We have those too. So back to the slides. Let's make a float variable. We'll be like y equals 3.14. That makes a box that holds 3.14. Now I can say print y, and then it'll, of course, print 3.14. Print the type of y. It knows the difference between an int and a float. It's going to say, oh yeah, that's a float, because it had decimal places. All right. I could have made this a float as well by saying 42.0. All ints can become floats. That's totally fine, but not all floats can become ints. So there's that. Yeah, so bool. Bool is for Boolean values. That's true and false, and those can be combined with your ands, ors, and nots. Remember that? All your conditional things, all your combinators. So the normal way to get a bool in Python is to be like 33 less than 34, like make a comparison, because that's going to be like Python's going to figure that out, yes or no, and the answer is going to be true or false, right? B1 equals. And you can assign that result to a variable if you really wanted to. So this is just a fancy way. 33 less than 34, that's always true, right? So this is just a fancy way of writing true. Does that make sense? And then, of course, you can hard code things like v2, have that hold false. And then you can print the values. Print b1, that'll, of course, print true, and b2 will print false. Right? Because 33 is less than 34, Python will figure that out and shove the value. It has to be a bool, and so it's got to get it down to either true or false once it's making that bool. And so this one becomes true, and then the other one is, of course, false because we made it false. And you can combine conditions with like ands and ors and nots, making new ones, things that you want to encode. So like print the result of b1 anded with b2. Print the result of b1 ORed with b2. Tell me what those are. So it's going to be what? True anded with false. That's false because you and anything with false, it's false. Only true anded with true becomes true. That's false. And then b1 ORed with b2, that's true or false. If you consult the truth table again, that becomes true. As long as at least one side is true, the whole thing is true for OR. Alright, so that's that. Again, just stop me at any point if you have any questions about stuff. So that's ints, floats, and bools. Str, right? Let's not forget about str. That's a string. Stands for a string of characters, and so it's like stuff that you would want to print. You put it between quotes. Those are your strs. Let's see here. So like S1 equals hello world. If I can spell. So there's a string S1, and Python, by the way, doesn't care if your strings if your strings use double quotes or single quotes. Like I can use single quotes instead. Doesn't care. And then Python knows the type, of course, of everything. What's the type of S1? It'll print str, And so this is where types are important, right? It knows that it's a str, not an int. So what can you do with floats and ints? You can use plus and star and all those things, and they work like numbers should. But if you do plus on strs, times on strs, because it's a different type, Python knows, and it'll be like, oh, you want to do stir addition, and that's different, right? S1 plus, you can add stuff. Print S1 plus all that, it'll make a new string. Bless you, with all of those exclamation points. Isn't that fun? So it's going to make a new string on the fly to print out with all those extra things. That's pretty cool. And then you can do multiplication on strings too. You can do string times a number. And that doesn't do normal math, it just duplicates the string. It makes a bigger string that has that original string 3 times in this case. All right? That's Python knows, like, okay, stir times an int, that does something special. It doesn't do int times an int stuff. It knows the difference. And then strings like know their length. There's a len function. Len of S1 tells you how many characters were in it. Apparently there are 13 characters in hello, comma, space, world, exclamation point. Okay? So that's strings or strs. A more general idea of that is lists, right? A string is essentially, you can think of it as a list of characters, individual single characters. But a list can hold a bunch of stuff of any type. So you can hold a bunch of numbers, for example, and use those angle brackets to make a list. So, for example, if I say this in Python, if I say L equals 2468, what does that do in memory? It makes something like this. It's going to have L reference the fact that it has a bunch of stuff. It's talking about a bunch of stuff at once, 2, 4, 6, and 8. And you can get at each of them through indices, right? Lists, first of all, they know their length. You can add them just like you could add strings. But lists have indices if you want something. Like I want to get the 2 out, that's index 0. I want to get the 4 out, that's index 1. 6 is index 2, 8 is index 3. And it also goes backwards. There's always 2 valid indices for every place. If you want the last thing, you don't want to care about calculating that index 3, you can just say -1. Go to index -1, that'll give you the last thing. So for this particular list, -1 and 3, those are equivalent indices. And then like you can do -2, -3, -4 to go backwards if you wanted to do it that way. But the normal indices, they start at 0 on the left and just get bigger. Okay, so that's lists. Let's make some list variables now and watch how they work. Let's be like L1 equals, I don't know, 5, 6, 7, 8, 9. So I made a list of 5 things. And I can print the whole thing if I want, as you would probably want to sometimes. It'll give me the whole list. But if I want a piece of that list, like I just want to print the 7, what index is that? That's 0, 1, 2. That's one of the valid indices. You can do the -1 if you want. But all right, if I want to get the 7 out, I can say L1 at index 2, go there. Give me that 7, please. So there it is, extracting it. And I can use that syntax to change it too. I can be like, you know what, L1 to 2, I don't like that you're 7, I want you to be 77. And so now that same syntax can set the value of the list. It can change things. And now if I print that same index again, now it's 77. And if I were to print the whole list, you'll see that it's 5, 6, 77 now. See that? So same syntax for setting and getting. Lists, let's see what else. Lists know their length, just like strings know their length. You can use the len function. Because really, strings are just a special kind of list, I would say. And you can use indices even in strings to get characters. So print the len of L1. How many things are there? There's 5 things, right? So it'll give us 5 back and print that out. And then I can make multiple lists. I can be like, all right, L2 equals the list 1, 2, 3, 4. And I can print, I can do math on lists, essentially. Lists have a plus operation, just like strs have a plus operation. But of course, it's not doing normal math. It's going to just add together the list. It'll build a newer list. So this will build up the list 1, 2, 3, 4, 5, 6, 7, 8, 9, and print that, because L2 was this one, and L1 was that one, and I added them in this order. Oh, sorry, 77. 6, 77, 8, 9. Does that make sense why we're getting all those things as output? Any questions about the different types? It's like the basic Python stuff that we need to do fancier things. All right, for my last trick for this file, let's do input. So what fun is it to run a program that does the same thing every time? Let's get stuff from the user. Let's have them to tell us what to do. So input is a function that you can call in Python, and it takes one argument. It takes the string prompt that you want to show the user as Python is getting that input for you. So input takes one thing. It's the string that it shows the user as it's asking them to type stuff. And then you press enter. The user, like, it lets the user type. They press enter. And once the function gives you back a value, it's giving you a string, whatever the user typed. So if you ask the user to type a number, you got it back as a str. So that's important. You might want to convert types if you need to. Input will print out a prompt, have the user ask the user for something, and then once the user presses enter, it gives you back what they typed as the return value from the input function, and back as a str always. So let's say like this. So let's ask the user input, what is your favorite number? Question mark. And usually I like to leave a little space here because it like asks the user to type on the same line, and now it'll be like over here away from the question mark, rather than like if you didn't do this, it would like have the user type right next to the question mark. We want them to type a little bit farther away from the question mark. And so you get this, and you can store that into a variable. That's totally fine. So what's your favorite number? 42. And so now that made the num variable. I just haven't used it yet. So let's like print it out. Print num. What's your favorite number? 42. And so printing num is like, yeah, it prints 42. But secretly remember that you're getting this back no matter what the user types. You're getting it back as a str. So what's the type of num? Even though it prints 42, oh, it's a str. So you can't do math on it normally as you might want to. So if you want to do anything, like let's say you wanted to give back the value times 2. Be like print num times 2. You'd expect that to be 84, right, if they typed 42? No, you're going to give back 4242 because it's a str times in it. That's not what you wanted, right? If you wanted to do normal math and get 84 back, then you needed to convert the type of num from a str to an int. So it'd be like, num, don't be a str anymore. I want you to become the integer version of what you were. So you just call the type as a function, essentially. So now, after this line, num is an int. And so if I print the type and try to multiply it by 2, it's actually happy this time. So let me show you that difference. So that type conversion is important. So, all right, it was a str, and it printed out something weird. But then on this line, we changed num into the integer form, whatever it was. It'll takes the str, changes it into an int, and then we're storing that right back in the num variable. And then we can print the type of that now, and it worked. It made an int, and then we can do times 2, and it does integer times 2, which is probably what we wanted here if we ask the user to type a number. Okay, so that, I think, is the last piece of the puzzle for basic types in Python. Any questions about that? Hopefully these files will be useful for you as you study for the final. Let's keep on trucking, and I think I want to talk about conditionals next. So if, elif, if else, if by itself, if else, all those things. So comparisons kind of drive the process. The idea is like you usually want to do one thing or another depending on values in Python. It's like, all right, hey, is x less than y? And maybe you got both of those from the user. Like, I'm not sure which of these is true. I'm not sure if this is true or false because maybe I got both of these numbers from the user. But I want to do one thing if this is true, one thing if x is smaller, and another thing if that's not true. It's like do thing 1 if this condition is true, do thing 2 if this condition is false. And that's kind of how I want to run my program, right? So comparisons produce Boolean values, true or false. Check for equality with double equals, not equal to, less than or equal to, you know all of them. I'll give back true or false, and you can use the results to drive your program, right? You can control your program based on the result using a conditional statement. So, for example, you have if else, or just an if. So, an if statement, for example, looks like this. You say if, then you give a condition here, something that results in true or false. Python will figure out if it was true or if it was false. Then you put a colon. Then you tab over, and your editor should do that for you. Like idle will do that for you. And then you give as many lines as you need of your body, that's what it's called. That's the stuff that you want to have run whenever that condition is true. Okay? So that's the goal, and that's how that works. So don't forget the indentation. And if we're good with that, I want to show you some examples. And here is the cheat sheet about that too. So here's conditional. So an if statement, it's like you got some code coming before and after that's unindented, like you lead into it. But how you execute an if statement works like this. The first thing Python does is it checks the condition, it runs it, figures out was it true or was it false. If it was true, it runs the body, and then once it's done, it goes to the after. Otherwise, if it's false, it skips the whole body, because you only wanted to do it if it was true, and then it runs after immediately. See the two options for an if statement? So it's pretty and color-coded. That's how that one works. And then if else, sometimes you want to do one thing if it's true, another thing if it's false. And the if statement just does nothing if it's false. But if you want to do something else if it's false, you do if else. So if condition, you have one body for your if, and then else, you have a body for your else as well. So it's like you're coming in from before. It's like the first thing this whole thing does, this if else statement does, is it checks the condition again. If it's true, it runs the body of the if statement. Otherwise, if it's false, it runs the body of the else. So it's either one or the other. And then after one of those bodies has run, the whole thing is done, and it runs your after code. So that's if else, remember that. And then you get even fancier with if else. Like maybe you have a bunch of different conditions to check. You just want to figure out the first one that's true. So if else is all about alternatives, right? It's like you have before, and then it's like if this is true, do the if body. Otherwise, if that wasn't true, it's like if it was true, do the if body, and then you're done with the whole darn thing. Go to the after immediately. Otherwise, if that wasn't true, try condition 2. Maybe that one's true. If that one's true, do that one. Do that body, else body. And then you're also done with the whole thing. Just find the first condition that works, run its body, and then you're done with the whole if else. You may have many elifs, by the way. And then finally, if you make it to this one, this is your otherwise, your final case. If none of those conditions was true, you're always going to run the else body. So one of those bodies is getting run, and then you're done. You go to the after. Okay, so that's the most complicated one. Hopefully the arrows are helpful. But yeah, let's have some examples on this. So let's do just some silly ones. Let's do one like, let's pretend we're a program for an amusement park ride, like at the Fresno Fair or something. So like, we'll make a program that asks the user how tall they are, we'll get their input, and we'll say whether they can ride the ride or not. Okay, so that sounds like an if-else to me. Like if they're tall enough, we'll be like, yeah, you can go on. Otherwise, if they're not tall enough, we'll be like, no, you're not allowed to ride the ride, sorry. So let's do something silly like that first. I'll make a new file and I'll call it conditional. So, all right, let's again. Here's our setup. You must be this tall to ride the ride. So let's ask the user how tall they are. Ask the user for their height. And so we'll be like, input, enter your height in inches, colon space. And that's a prompt, and we're going to get that back as like a height variable. And so we know we're going to do number stuff with this height variable, so we should just convert it immediately. I don't know of anyone who tells people that their height is exactly 60.75 inches. Let's safely assume that the user is going to type us an int rather than a float, but if you think that they could do like 0.5, say float there. But now I'm making a number out of the height. All right, so I was getting it as a string. This whole thing will result in a string and a stir, but I want to change it immediately into an int so that I can do number stuff with it. All right, and so let's say that you got to be like 4 feet tall to ride the ride. So if height is less than 48 inches, right, then print, sorry, you can't go on this ride. Sad face. Otherwise, that means this wasn't true, right? If it was false, that means your height is at least 48 or greater. So else, print, you can go on the ride. And remember that you can use single quotes or double quotes for your stirs in Python. Doesn't care. You can go on the ride. Exclamation point, happy face this time. All right, so that looks like a program to me. So we'll be like, all right, enter your height in inches. I honestly don't remember my own height. It's at least 60 inches, so I can go on the ride. Cool. I have to do some math. Enter your height in inches. Let's say that we are young and we're like, we are 38 inches tall. Darn. we cannot go on the ride right now. So it's either one or the other. This body or this body that's getting run, depending on the result of this condition. If it's true, it'll run this body. If it's false, it hits the else. Any questions about that? That coming back to us? So you will almost certainly be forced to write a conditional statement on your final. All right. Let's see here. I didn't want that. Let's have a more complicated example. Let's do the grade calculator. I showed you that once. Let's do that again. This is going to involve a bunch of elifs, right? So that we try a bunch of alternatives. Because we want to do something like this. Like if it's an A, like check. The first thing it could be was an A, right? If that's true, print, hey, yeah, it's an A. You get an A and we're done. Otherwise, if it wasn't an A, like it wasn't greater than or equal to 90, now you got to see like, okay, is it a B, C, D, or F? You still got to check a bunch of things potentially. So then you're like, all right, maybe it was a B. If it's greater than or equal to 80, then if that's true, then we know it was less than 90 because we got here. It's greater than or equal to 80, it must be a B, so we'll print out B, then we're done. Otherwise, if that's false, you knew it was an A, and it wasn't an A, and it wasn't a B, now you got to try a bunch of stuff down here for C and F. Okay, so all those alternatives end up being elifs. All right, and you're checking your conditions in order, like I was saying on this cheat sheet. So we're going to have a bunch of elifs, as many alternatives as you want. It's just going to find the first conditions true and run the body, and then it's done with the whole darn thing. All right? Or if none of them is true, it's going to go straight to the else. Or it'll make its way to the else is what I should say. All right, so let's do that. Let's do a grade calculator. Let's be like grade equals. Let's get the grade from the user as an input. Enter your grade as a percentage, colon space. And grades are usually, those usually have decimal places. So let's make a float out of that because we want to do math stuff again with it. So all right, our grade is in a variable and it is a float, so we can do number stuff. It's not a stir anymore. And so now we want to check, like, is it an A, B, C, D, or F? We want to print out which. So the proper order is do the hardest thing to do first. So if grade is greater than or equal to 90, because maybe you got extra credit, like it's bigger than 100, that's totally fine. So as long as it's bigger than 90, you got an A. Right? So print A. Does that make sense? So that's your first thing to check. And then otherwise, like, you can't just have one out. You could have one else, and you have to make a bunch of nested if-else's, which is kind of ugly. Once you get here, right, that means, well, it wasn't an A. That's all you know. But you still need to check, like, was it a B, a C, a D, or an F? Because you're trying to print out a grade. So that's where elif comes into play. It's like, all right, if it wasn't that one, if it wasn't greater than or equal to 90, so I know if I got any further, it was less than that. What's the next hardest thing that it could have been? Grade greater than or equal to 80. All right, so if I ever get here, then it wasn't greater than or equal to 90, so it was less than that, at most 89.9999. If it's greater than or equal to 80, though, then, and it wasn't greater than or equal to 90, that must mean it was a B, right? It's between 80 and 90. Does that make sense? That's the next thing you try. And that's like, you read elif as otherwise. Otherwise, if this is true, it's a B, and then you're done. Otherwise, if that wasn't true, then you know it's less than 80. Well, all right, maybe it's a C then. I gotta check. So, okay, if it was, we skip this guy because this wasn't true. Maybe it's still bigger than 70. If so, that means it, like, because this was false, it was less than 80. If this is true, that means it's greater than 70. So that means it's C. It's between that range. See that? And then a couple more. So, all right, otherwise, if that wasn't true, maybe that means it's smaller than 70, but maybe it's greater than or equal to 60. You kind of do have to do it in order if you want to make this look normal. If that's true, if we got here, like, all right, that means this wasn't true, this wasn't true, this wasn't true. So it's less than 70, maybe, but if it's greater than 60, it's a D. And finally, else, right? Because if this wasn't true, that means it's at most 59.9999. And anything smaller than 60 is an F. So that could be your else case. And that is your F grade. Does that make sense? That's going to be how you would check that. Yeah, question. Essentially, if you just want to say like otherwise, if nothing was true, you put an else. If your only options were this many and like it was invalid to have something smaller than 60, then you don't even need the else. Sometimes you don't have to include it if it's not necessary, but usually it's like a catch-all. It's like if nothing else worked out, most likely you're going to want an else there. It's like either alert that there was an error or give the last possible option. Yeah. So let's see, enter your grade as a percentage. If we got like a 95, it's an A. But maybe if we got a 75, it'll skip if you're like, all right, 75 is not greater than or equal to 90. It's also not greater than or equal to 80, but it is greater than or equal to 7. It'll find the first one that works. And so that's why it will correctly print C. See that? Same for D and F, like 65 or 60, I don't know, 62.25. It will figure that out. Like, all right, that's not greater than 90. Neither is this true. This is not true. Oh, but this is the first thing that works. So it must have been a D. See how the ordering is going to give you the right answer there? If you did these comparisons out of order, one might take precedence, and you do have to worry about that. And then 55%. Notice that you couldn't have had like the D check first. Like, boop, if I did this backwards, like I did a D down here, like a 90 up here. Do you see how this is going to print D for anything, even if it's an A? Like, this is the first thing that works. All right, that means if the grade was 105%, it'll print a D, because that is greater than 60. It's just finding the first one that works. So you do have to worry a little bit about the ordering. But, yeah, as long as you go from like the hardest thing that's possible to the easier things, that's it's going to work. Usually, if you have a range like this, you can just memorize this kind of order. But yeah, I think that's conditionals. Any questions about that? Any other questions, I mean? Not too horrible, I hope. Definitely study all this, though. Now let's talk about loops. Right? So there are two main kinds of loops in Python. There's while and for, and I guess I have slides on each of them right now. So let's do both of those, and then we'll call it a day. So while loops, I have a page for that. So a while loop looks like this. It's always, it kind of is like an if. So while you got a condition, then it's got a body. So it's going to run the body as long as the condition is true. All right, so it's going to jump into the while loop. The way that the while loop works is it always runs the condition. If that's true, it runs the body, and then it goes and it checks the condition again. It's going to keep on doing that until the condition becomes false. The second the condition is false, maybe it's even the first time, then it's done. Then it stops. All right? And that idea, that ability gives you looping. It allows you to come back around on the body a bunch of times. All right? So let's do an example where we print all the numbers from 1 to 10. Let's see. And then I'll show you break, because that'll be useful one day. So how to print all the numbers from 1 to 10? Let's do it as a flow chart first. Be like, all right, I need a variable called I, your standard iteration variable, and then I want to make a loop. I want to print all the numbers from 1 to 10, so I want to do this. I'll be like, all right, as long as I is less than or equal to 10, I want to print it. So if that's true, that's your comparison. If that's true, I want to print I. That'll print it. And then I also want to increment I, so that when I wrap back around, it's a different I. It's like 2 now, 3 now. Just keep on doing that. So print 1, print 2, print 3, print 4. It'll just keep on printing it, making it bigger until I becomes 11. I do not want to print 11. I'm done at that point. So once that becomes false, then I do the rest of my code, which I called after in my cheat sheet. So I'll call it after here too. So yeah, that's that. So let's turn this, right? Go from this idea to the while loop. And I'll make a file called loops.py, I guess. So, gosh. So I want to translate that to code. So I want to be like, all right, so I equals 1, and then while I is less than or equal to 10, as long as that's true, I want to print I, and then increment I equals I plus 1. Yeah. See that? And so that will legitimately give me printing from 1 to 10. Do we see how that's going to repeat? I starts at 1, print 1, 1's less than 10, print 1, make it 2, and then wrap back around. Check the condition again. 2 is less than 10. Cool. Print 2, make it 3. 3 is less than 10. Print 3, make it 4, all the way to 10. 10 is less than or equal to 10. Print 10, make it 11. 11 is not less than or equal to 10. So we're done. Then we stop. Okay, so it needs to get bigger. This eventually needs to become false. That's what stops loops. Okay? There's that. You can combine ifs and loops. It's all fun. You can put whatever you want in a body. One thing I don't think I showed you yet was break. There's a statement in Python. You just say break on a line by itself, and that stops the loop that you're in. So if you ever want to stop your loop early, you can say break. Let me show you that. Let's say that like sure, we were normally printing from 1 to 10, but let's say like we want to stop early, like for some reason, like I hate the number 9 or something, or I hate the number 8. So if I ever becomes 8, you can stop early with the break statement. You just say break on a line by itself. So this will be like, all right, I plus 1, okay, if I just became 8 right here, break out of the loop, and that'll stop the loop and it won't continue. So it goes only from 1 to 7 now. So we hated the number 8, apparently. So break stops the loop, and that'll be useful in just a second. I believe I will use an example of that soon. But that's a while loop in general. Let's do another example that's a bit more fancy. Let's do one where we sum up all the numbers that the user gives to us, that the user types up, until they type -1. Let's say as long as the user gives me a number that's not -1, like that's the stopping number. Every number that they can type as many as they want, and I'm going to add them all up until the user types -1. So they'll type like 42, 43, 44, 1, 2, 3, 4, 5, as many numbers as they want to type and want added up. And then once they type -1, then I stop. Then I break out of my loop. Okay, and then I'll give back the sum of all the numbers that weren't the -1. The -1 doesn't count. We don't add that to our sum. It's just that was our stopping number. That told us when to stop. Okay, so yeah, let's do that. Let's make a program that keeps track of a sum of a bunch of numbers. Boop. So all right, so I need to keep track of the sum eventually in a variable. I'll call that like total. I'm keeping track of the total value of all the numbers summed up. And then I need to keep getting numbers from the user that I want to sum, right? So I'll call it next num equals, let's ask the user for the next number that they want added up. Enter the next number, or -1. And let's assume that the user's only given us ints. So let's convert this to an int. So when we want to do number stuff, right, we're going to add it into total. And then while I keep getting a number that isn't -1, I want to keep going. So I want to add next num, it was -1, add it into the total, and then get the next number. Put that in the next num, because maybe that one's going to be -1 and they wanted us to stop. There's a way to do it without break even. So this number was not -1 that I just got, so add it into total. Total equals whatever it was plus next num, and then I want to just loop this process. I got to get one number to start us off outside the loop, but then you just keep getting a new one inside the loop like this. So I get the next number, store it in the next num. So like I type 1, 2, 3, they keep getting added into total, and I get the next one, and as long as it's not -1, I'll add it into my total and ask for a new one. But the second that last number was -1, this comparison will finally be false, right? -1 is not unequal to -1, it's equal. So it'll stop the loop, and then I'll be done. And outside this loop, I can be like, all right, your total was blah, blah, blah. So when we get here, the only reason that this loop would have stopped, right, is if this condition became false. The only way for this condition to become false is if next num is -1. When we get here, next num must be -1, and we'll output the sum in just a print statement. Be like sum colon space is total. So there's that. So let's run this. So enter the next number, or -1. I want to enter, I don't know, 42, 43, 44. As long as it's not going to -1, it's going to add that into the total variable and keep on asking me for something new. 1, 2, 3, and then let's say like I'm here, sitting on this next num line, it's asking me, and I'll type -1 now, and then it's going to be like, oh, when it wraps back around to the condition, because that's what while loops do, it'll notice that it is -1, and it'll stop the loop and get out here to this print line and be like, your sum was 135. So it's apparently the sum of those six numbers is 135. I trust that. Any questions about this program? And add up a bunch of stuff until the user types -1. You see how we're using the while loop to say, as long as that number isn't -1, I want to keep adding it and getting a new one. Once it is -1, that should stop me. So those are loops are just a generic way to wrap back around on the same code. A while loop is the most general kind of loop, I would say. So that's why we learned it first. And then for is a different kind of loop that kind of goes through something. It iterates through something, and I want you to think of that something, in this class at least, as a list. So there are special functions like range that gives you back a list-like thing. You can convert it to a list or just think of it as a list. It gives you back something that you can go through with a for loop. And range 50, if you just give it one argument, it starts at 0 and it goes up to, but not including this number. So it'll give you like a list that holds 0 to 49. All right, so I can show you that in the REPL. So range 50, if you just type it, it like doesn't build the list because it doesn't want to waste memory. But you can be like, okay, make a list really out of the range 50. And so then it will give you the list from 0 to 49. So that's really what it's building, and you can go through that with a for loop. So, I don't know, example, let's find the minimum of a bunch of values in a list that the user enters. So let's build up a list and get that from the user. And then we're going to print that list, and then maybe we'll also print the minimum thing. Okay, so I'll show you that. So yeah, for loops iterate things, usually lists. So like if you have a list L and it holds 1, 2, 3, you can go through it in a for loop. You can also make lists easily if you want stuff in order with a range function call. Like a range of 50 will generate the list 0, 1, 2, all the way to 50. All the way to 49, excuse me, not including 50. And then, so let's get a list from the user, and then we'll also calculate the minimum value in that list. So I got a few ideas here. Dot pi. I kind of want to do this same kind of thing, like get a number so that I can put it into a list. So maybe I'll copy a lot of this code. I will use a while loop to fill the list at least. So let's build a list. L equals empty list. And so the idea is I'm going to get a number from the user. I'm going to add it into the list L, every time I get one, as long as it's not -1. So L equals whatever it was, plus a new list with just that new number. So it'll build up a bigger list slowly but surely. And so by the time this loop is done, it will have filled up L, print L. So this is a while loop that's going to fill up a list. You see how I changed the other one to not just add to a sum variable, but to add to a list now? So like, I don't know, 5, 6, 7, 8, -1. That built up 5, 6, 7, and 8 into the list L. So now L holds 5, 6, 7, 8. All those things that I typed, all those things that I typed in order. Isn't that fun? There's that. And now I would like to show you a for loop that uses this list. It goes through the list and it finds the minimum value. Okay? So here's the setup. I can't remember if I've told you how to do this already, but I'm going to explain it again, even if I have. So to find the minimum or the maximum value in a list, what you do is you kind of guess. You make a variable, you call it min, or whatever you want, and you make a guess. Like, say your list is this. Say your list is 3, 1, 2. What you do is you make a guess and you update your guess for the minimum. So imagine that this was your list L, and you're trying to find the minimum of it. What you do is you guess that the first element is the real minimum. So you're like 3. Put 3 in the min variable. That's your guess. That's your initial guess for what the minimum of the whole list is. And it's not correct yet, but at least it's a value in the list. So then what you do is you go through the whole list. You see the 3, it's like, and you compare what you're at to what is in the min variable. It's like, all right, 3 versus 3. They're the same. They don't need to change. Advance. 1 versus 3. You always, as you go through the list, if you find something smaller, that's a better guess for the min. So update your guess. All right, 1 is smaller than 3, so I'll replace the min with 1. And then I'll keep on advancing through the list. All right, 1 versus 2. 1 is smaller. I'll keep that as my min. And do you see how, if you go through the whole list, give each element a chance at like beating up the minimum and winning, by the end, you're going to have the real minimum in the min variable. You're always going to save the smallest thing. It will be the true smallest thing, assuming you've gone through everybody. So, yeah, that's the setup. Guess that the first element is the minimum, then go through the list, update your guess as necessary, and once you've gone through the entire list, the real minimum would have won out. So you have the true minimum in the variable now. So let's program like this. We'll say, so make a guess. The first thing you do, make a guess that the min, the real min, is the first, no, sorry, you can't see this, is the first element of the list. So I'll be like, all right, the min is equal to L of 0. I don't know if that's true, because we just got this list from the user, by the way. We don't even know what's in this list. But just guess that the first thing is the minimum. And then, maybe that is the true minimum, we don't know. But go and give everybody a chance at winning out, compare it to the minimum variable and update it as necessary. So loop through every element of L and update our guess if you need to. Right? So here's how you go through a list in a for loop. I got a cheat sheet page for that. So here's how it works. You say for, you have a variable name, and you say in, and then you give some list-like things, a range or a real list variable. And so what it's going to do is it's going to set this variable equal to the next element in the list. As long as there's another element in the list that you have not visited yet, it's going to go through them from left to right. It'll set that variable name to that next element, and then run the body with that being set. And that's what's going to be repeated. As long as there's something else in the list that you haven't seen yet, it'll set the variable that you say, give it a name equal to that, and then run the body. We'll keep doing that as long as you still have an element that you haven't seen yet. And then once you've seen every element, it's done with the loop. It goes through the whole list from left to right. That's how that works. So I'm going to say something like, X in L. So every element of the list L is going to be called X from left to right. And so what we want to do for every X value, for every value that we see in this list, if X, we're going to compare it. If X is a better guess for the min, then update our guess. Min should be set to X. That's a better guess. Maybe it's the real min, or maybe it's going to make its way towards it. All right, so that's the game you play. Just guess 3, then try the 1, then try the 2. It's one of them is going to win. Keep on updating it. So if the value that I see at the list right now, if X is smaller than my current guess for the minimum, then it's a better guess. And the minimum maybe is X. It's closer. It's a better guess. Maybe it's the real minimum. Maybe it's a better guess. Either way, I'm closer to the true minimum if I do that. And then if I do this for everybody, I let everybody win out. If I try every value of the list, call it X. One of these really will be smaller than everything else, and it will run this body for that one and be like, oh, the min is set to that, and then it will never be any smaller, so it's going to stay that. And eventually, by the end of your list, as long as you visited everybody, you will find the min, right? So this will stop once it's gone through the whole list. So we unindent after we're done. Now min holds the true min. Now, I hope that logic makes sense to you. So min colon, and then here's the min value. So let's enter our list. I don't know, 3, 1, 2. That's our list, and it will correctly find that the minimum is 1. And you can do it backwards. Like the hardest one is always when it's backwards, like 8, 6, 7, 5, -1. So you see how it's gonna correctly find that the min is the last element, but it'll take a while to get there. It'll be like 8. That's the first guess. Oh, 6 is better. 6 is still better when you see 7, but then 5 wins over 6. So that's how it's going to play that game. Does that make enough sense? How it's going to go through this list and have every element fight every other element for that min value. And the smallest one will win. Same with max, right? Just change this to be greater than. Just find the greatest thing. Keep on updating when it's bigger. So there's that one. I think that's a good example of a for loop. Just going through the whole thing, all of L, and you call every element X. They all get a chance at being X. All right. Yeah. One last example for the day. Let's do this one. Because we noticed that it's a really cool, powerful concept. You can prove theorems by writing programs, which is so cool. So here's a theorem that we can prove. Let's prove that there exists an X that is between 32 and 37 and is prime. See how I'm reading that? This is a statement. It's either true or false. Let's prove it true by finding an X that is between 32 and 37 that is prime. Does that make enough sense? This This is trying to claim, like, this is true if there exists an x such that x is between 32 and 37 and x is prime. So let's search for that value by looping through the numbers from 32 to 37 and seeing if any of them are prime. If we find a prime, that's a candidate for our x value, and it will have worked. So let's prove our theorem by writing a program that just searches through those values, those valid potential values. So for n, let's call it n, for n in range 32, 38. This will go between 32 and 37. I'll make a list between 32 and 37. This will iterate from 32 to 37. Let's see how I can show this to you. Let's make it smaller. There. So we'll iterate from 32 to 37, and then call every value n. And I'll be like this. I'll be like, if that value of n is prime, let's make like an is prime function. If is prime n, if that's true, then print the statement is true. And because it just found a value between that range that is prime, it'll be like print that value. Print n is prime, exclamation points. Something like that. Do you see, if we had an is prime function, by the way, do you see how this loop would find a value that could serve as the x in this statement and prove it to be true? So that's pretty cool. This proposition is another name for that, right? Proposition with a quantifier. So yeah, let's make an is prime function, because that's the last piece of the puzzle. I won't test you on this for sure. I'll teach you how to write functions. We'll go over function writing next time, but I just need an is prime function to make this work. So I'll very quickly make a function called is prime. We'll talk about functions in detail next time. So def is prime, like asking me if num is prime. What does that mean? One way to check if a number is prime is to try every number between 2 and that number minus 1. It's kind of a silly example, but try every value between 2 for 4 n in range, 2 and that number minus 1, so 2 to num, and see if you can divide the number by that value. If you can, and there is no remainder, that means you found a factor other than 1 in the number, right? Prime numbers must have only factors of 1 in that number. Anything else means it's composite. So if you try any other number that's not 1 or the number, and you find that it goes in cleanly when you divide, that there's no remainder, that means you have found a counterexample. You found a factor. So if num mod n, if you try to divide and the remainder is 0, that means it is not prime, return false. Otherwise, if you get through every possible value, you can say return true. And actually, because you're just looking for one factor, again, I'm not going to test you on how to write an is prime function, but for your knowledge, you don't actually have to go up to num minus 1, because you're just looking for one factor. It's guaranteed that if there is a factor, it will be between 2 and the square root of the number. Just like that, the square root squared is the number, like that's you're just finding one factor. So on the smaller side, the biggest possible factor would be the square root of the number, so num to the 0.5 power, make an int out of that, and then add 1. This is kind of disgusting, and you don't have to understand it, but that's a faster way. You go through less numbers this way. But the idea is you're looping, and you're trying to find a number that divides this number, trying to find a factor. And if you can't find a factor, it is prime. But if you do find a factor, it is composite, so it's not prime. You return false. Okay. I will not test you on this code, but that is on this function. But it's an interesting idea. Oh shoot! What have I done wrong? Oh, I forgot the opening parenthesis. There you go. And so, I don't know, I still have to do the first loop for this second loop to run. So I don't know, let's make 3, 1, 2. And then it's going to do the rest. It's going to be like, statement is true because it gets there. It gets to 37. Apparently 33 and 35, those are composite numbers. I guess, yeah, 33 is a multiple of 3, 35 is a multiple of 5. But 37, oh man, that is a prime number. It's within the right range. So that proves our theorem, proves our statement to be true. Yeah, and so you can use a program to search for something that will make your statement true. And so we made a program that solves this proposition, proves it to be true. Our program became a proof, which is kind of fun to think about. Any questions about that example? So it's just a more involved example of for loops, I would say. For loops are just going through stuff. What are you going through? Call that thing n or x or whatever, and run the body with that value, going through every value from left to right. And so yeah, once you've done that, you have looped through everything, and you can stop executing, go to the rest of your code, go to the after section. And I think that is for loops, and that is all that I wanted to say. This is a good place for us to stop. There's, of course, more Python to go through. We need the turtle library. We need to review that. We need to talk about functions. But that will be a problem for Wednesday.